Okay, so we want to calculate how much more heat 10 grams of ice is to, or less than, vaporize 10 grams of water. So we've got 10 grams, and it's 80 calories per gram for heat of fusion. So we're looking at 800 calories. And then we've got 10 grams and 540 calories per gram. So we've got 5,400 calories. So minus 800 calories, and we get 4,600 calories. So our answer is 4,600 calories. That makes sense? Along the same lines, if for some reason you were going to be burned by 10 grams of 100 degrees Celsius water, which would you rather terrible thing happen to you? Somebody puts 10 grams of 100 degree water on your arm, or you get hit with 10 grams of 100 degree steam. Which one would do less damage? Why the water? You are correct. So you can think about it being the opposite. You can go, how much would it take to go more? But if I'm steam, what has happened to me? If I'm 10 grams of steam, sorry, go ahead. You've been vaporized. Didn't we just calculate it's 5,400 calories to vaporize that? So if I'm steam, the first thing I do is I hit your skin and I condense. And I turn from 10 grams of steam into what? At 100 degrees Celsius, right? So you don't want to start with the steam if you could have just started with the water, because you could have avoided getting 5,400 calories put it into your arm. Does that make sense? Do you see why steam is quite dangerous? If you take a lungful of steam, you die almost immediately because you go into shock. And when I say steam, I actually mean vaporized water. I do not mean that stuff that comes out over the top of a pot of boiling water for spaghetti. That's already cooled down the moment it's left the surface. I'm talking about actual 100 plus degree gaseous water, because it's going to give all of that energy back to whatever it's taken. So if it hits the air sacs in your lungs, what's it going to do to them? It's going to give a bunch of calories of energy, and those air sacs are not prepared for that, right? They want it to be a particular, I mean, your lungs hurt if it's too dry out. They're not ready to have an extra several thousand calories or kilojoules of energy added to them. All right, so we want to run through this Hess's Law problem. The first equation is backwards, right? So I'm going to need to go 3 M's and N2 gas, and then change the sign right there, so we do. So all that's gone. And then the next one is backwards. I'm just going to write CH4. That turns into carbon solid and 2 hydrogen gas. Swap that sign. And then the next one, I don't know, because there's nothing in it that I want, right? No, there's hydrogen. Also, backwards, jerk. HCN gas, 2, 2, 2, 2. Cancel all that stuff out. And make that negative. All right, so Issues? What do we got to do first? That guy's okay. We want that right there.
I think for the bottom equation, I don't think we want to flip it. We have to have the HCN on the right side.
Oh, my bad. I was looking at the hydrogen. You're correct. Let me kill that. Do that. We need that right where it is. So what else do we need where it is? We need that where it is. And then we need the hydrogens, right? That guy there. And I guess this guy here. Okay, so we need the carbons to cancel out, the nitrogens to cancel out, and the hydrogens to cancel out. So what do we want to do first? Or a hydrogen to cancel out. Let's start with the first equation. What's wrong with it?
Too much NH3.
Too much ammonia. We okay with that? So if I divide the whole thing by 2, so that goes away. This turns into 3/2, and that's a half. And then I divide that value by 2. Let's not forget that. So then then this guy is the way I want him to be. All right, so what about the next one? That one's correct the way it is. And then the bottom one, also too much, right? So I got to divide this whole thing by 2. So divide you by 2, divide you by 2, that goes away. You become a half nitrogen, you become 1, and you become a half hydrogen. Okay, so now what am I going to do? I want another color. This guy right here can cancel out with that one right there. The half nitrogens. Okay. Carbon, there's 1 carbon here as a product, there's 1 carbon here as a reactant, so those guys cancel out. Do my hydrogens work out? I mean, they must. I want 3 hydrogens, and what do I have? I have 3.5 hydrogens. We okay with that? So everybody see that? There's 2 hydrogens here, and there's 1.5 hydrogens here, but there's a half hydrogen over here, so that half cancels out with that, makes that a 1, and that leaves me with 3 hydrogens. That was just a mess up there. Okay. So then we'll just add these guys up. $91.8 divided by 2 plus 74.9 plus 270 divided by 2. 256. That work? We're good with that? Okay. Alrighty. Give the electron configuration for magnesium ion and selenide. Okay. So what is it? No periodic table in this room. What number is it? Just what element number is it? 40? 34. Okay, so we're at 12, so 3p6, 4s2, 3d10, 4p6. Is that right? We okay with that? So since selenium is right here, 34, I'm trying to get up to krypton. How do I know I'm supposed to put 36 electrons in here? How do we know that this is going to be a 4p6 and not 4p4? How did you know that this was supposed to stop at 2p6 and not 3p3, 3p2?
Because magnesium is giving 2 of its electrons to the selenium.
Yeah, but I didn't even ask for that, but it could be giving 2 electrons to selenium. The key to this is it says magnesium ion.
So you can't just write that it's not, it doesn't stop at 3s2.
It doesn't stop at 3s2 because that's the electron configuration for magnesium atom. This is magnesium ion. So when magnesium forms an ion, I pick magnesium specifically because it forms one ion. What ion does it form? Based off of its position on the table. Two plus 2 gives those 2 electrons away. So that's why I've got magnesium with a +2 charge, and it's got neon's electron configuration because that's the closest noble gas. So because it says magnesium ion, you know you need to turn that into an ion, which makes you have to pick its most stable ionic configuration. And in this case, if I'm magnesium, I only have one ionic configuration, and that's me dumping the 2 electrons that I don't want. Why is the selenium, how do I know that it's supposed to be 4p6 over there? It doesn't say selenium. What does it say? Selenide. What's the difference between chlorine and chloride? If it's I, that means it's already gained its electrons. I don't have to say selenium ion because the IDE is inferring the fact that it's gained electrons and become an ion already. So this is most likely configuration would be to grab 2 electrons to look like krypton. And so then I also identify that that has happened with a +2 charge here and a -2 charge here. But these guys would like to make a compound, right? I mean, MgS would be a nice compound. +2, -2, easy. You have any questions about that? Anybody? Makes sense. All right, so what and why is it happening when electrons, 2 electrons in a polar bond? What's happening to the electrons?
They're being shared between 2 atoms, but one atom has a stronger affinity for the electron than the other atom.
So what's happening to the electrons?
They're closer to one atom than the other one.
Can you say that's shorter? Maybe 2 words? How about that? So me saying this uneven sharing of electrons, it restricts you to what kind of bond? It has to be covalent, right? Because you don't have any sharing at all in an ionic bond. All right, why is this happening? And I think that's the first thing that you said. So whoever has higher electronegativity, that's how you know which of those atoms likes the electrons more. Okay, well, we kind of just answered that, right? This has to be covalent, or the only ones that can be polar and ionic cannot be polar, and this is because ionic has no sharing. All right, how about these bond strength differences between fluorine, oxygen, and nitrogen? It's not a hard question.
Oxygen has a double bond, nitrogen has a triple bond. Fluorine only has a single.
Yep. That's part of it. What, you guys remember what the other part was? How many electrons is a fluorine atom trying to get? Just trying to get one electron, right? And the oxygen?
2.
And the nitrogen? It's easier to just get one electron than it is to get 2 electrons or 3 electrons. And coupled with the fact that I'm connected to it multiple times makes nitrogen the most difficult one. Nitrogen's really close to a noble gas as far as its ability to not react with stuff. Okay.